Profit-based units scheduling of a GENCO in pool market using deep reinforcement learning. Abstract: the primary objective of power generation unit scheduling for a GENCO operating in restructured power system, is to maximize accumulated profit over the entire period of operation. When operating in the pool market, GENCO's demand is the spot market allocated energy. Hence, prior to unit scheduling, the GENCO has to forecast how the market will be as far as the market clearing price and the spot market allocation for each hour of the day is concerned. By using these two market signals, the company can optimally schedule its generation to maximize profit. However, this paper aims at exploring capability of deep reinforcement learning, DRL, established by using Deep Deterministic Policy Gradient, DDPG, algorithm to optimally schedule generating units in order to boost GENCO's financial benefit in deregulated electricity market environment. Simulations were carried out for a GENCO with 6 generating units each with different operation cost curve and different generating capacity. The resulted output reveal that the proposed method can be applied to solve profit-based generation units scheduling problem, PBUS. Keywords: DDPG, DRL, Market Clearing Price, MCP, Profit-Based Unit Scheduling, PBUS, Power System Deregulation. Introduction. The deregulation process in energy sector is one of the most important transition for modern electricity industry. This transition enhance the competition in the electricity market. The power prices are likely to descend, which favors the electric power consumers 1, 2, 3. With such idea in mind, there is a need to optimally schedule the generation units in a manner that will generate more profit for. This is due to the fact that this type of market is based on competition which affects the electricity energy price. In contrast from vertical integrated power system, where utilities had obligation to meet demand and reserve, in deregulated power system the main objective of GENCO is to maximize its profit 5, 6, 7. That is, GENCO has to schedule its generation pattern that will maximize the total profit. On the other hand, the responsibility of independent system operator, ISO, is to satisfy the system power demand in order to balance between generation and load. The ISO neither owns nor operates any generating unit but receives bids from different GENCOs and it decides energy demand among the GENCOs based on a cheapest first method 8. UC problem has been solved by several methods, each with its advantage, S, and disadvantage, S. 6,9 Explain the priority list method, dynamic programming 10,11, Lagrangian relaxation, genetic algorithm 12, Gray-Wolf optimization 13, particle swarm optimization 14, taboo search method, fuzzy logic algorithm 15 and evolutionary algorithm 16. However, a few reactions have been rooted to these strategies as they are iterative, require an initialization step that can cause the convergence property for the pursued interaction into ideal local optimal solution. Also, they may neglect to tackle the powerful case including above limitations. Market clearing price and the load forecasts plays an important part in strategizing optimal bidding in a day-ahead market 5, 6. The reinforcement learning technique has been used to solve complex problems and high-dimensional problems in control systems 19, delivery route problem 20 and robotics 21. The aim of this study is to introduce the use of deep reinforcement learning to solve optimally scheduling of generating units scheduling in deregulated power system environment in order to maximize GENCO's profit. By analyzing the operation predicted data, the market clearing prices and market allocations, a data-driven profit-based unit scheduling, PBUS, model is established. By means of DDPG algorithm, the established model is trained to maximize the GENCO's profit. Finally, the model is tested to show the effectiveness and accuracy of the proposed method. Problem formulation. The objective of the PBUS problem is to formulate a scheduling pattern that will maximize the expected profit for the entire operation period. Therefore, the objective function is expressed as the difference of revenue generated and costs spent 22, 23. The optimization problem for PBUS can be formulated mathematically by the following equations. The proposed method. Reinforcement learning. Reinforcement learning is a class of machine learning that is based on trial and error, that is concerned with sequential decision making. 24. An RL agent exists in an environment. Within the environment it can act, and it can make observations of its state and receive rewards. These two discrete steps, action and observation, are repeated indefinitely with the agent's goal being to make decisions so as to maximize its long-term reward. Deep reinforcement learning. DRL utilize deep neural net as function approximator, which are especially valuable in reinforcement learning in the case that observations and/or actions dimension are so high that one can't even think about being totally known. 25, 26. In the deep reinforcement learning, deep neural network is utilized to implement either a value function, or a policy function. I.e., networks can figure out how to get values for the given states, or getting values from actions and observation sets. Instead of using the technique of Q-table, which would be very expensive method, one can train a neural network from the given dataset of states or actions. Examine how significant those are comparative with our target in reinforcement learning. 27. Like every neural network, coefficients are used to estimate the function relating inputs to outputs, and their learning comprises to tracking down the correct coefficients, or weights, by iteratively changing those weights along gradients that guarantee less error. In reinforcement learning, convolutional organizations can be utilized to perceive a specialist state when the input is visual images. Figure 1 is an architecture used to design both actor and target actor networks. The network model constituted of feature input layer, 4 fully connected layers, which are all feed-forward neural networks, and 4 activation functions. The algorithm uses a total of 4 neural networks. The first network is called the actor, where denotes the network parameters. The actor part of the DDPG agent is classified as a policy search method. The second network is called the critic, where denotes the network parameters. The critic part of the DDPG agent is classified as a value function method. 28,29. DDPG uses target network idea to implement further 2 neural networks, one for each of the actor and critic networks. The network parameters for the actor and critic target networks are denoted as n respectively. DDPG also makes use DQN's experience replay buffer to store experience which is randomly sampled from during training. 30. The loss function for the critic network is similar to the DQN loss function except that actions are selected by the actor network. 31. Using the standard Q-learning update and the mean square error, the critic loss function is expressed as the algorithm needs to give action command for each generating unit that will satisfy all the constraints and meet the objective. The model is initialized by randomly selected power distribution coefficients for generator 1 to 6 as in Table 2 below shows the initial operation parameters and Table 3 shows the DDPG algorithm parameter setting. Example analysis. Simulation environment. The GENCO mathematical model was developed in Simulink environment, constituted of an RL agent block, reward calculation subsystem and observation subsystem. The deep reinforcement learning based on deep deterministic algorithm was created with the architecture explained in Figure 1 and Figure 2 for actor and critic respectively. The implementation was done by the help of Deep Designer app of MATLAB R2020B version. The setting parameters for the neural network architecture are tabulated in Table 1. Data used for training and testing the model. During training, the random time series data generator was formulated. This is to ensure good generalization of final result. Also it serves the purpose of large data set. The standard IEEE 118 bus system data from 32 were utilized to test the trained RL agent. A single GENCO having 6 generating units of the 54 thermal units in the IEEE 118 bus test system and the generating units data are given in Table 4. The input data to the model were 24-hour, day ahead, the time series predicted market clearing price and the predicted spot market allocation for the GENCO data as plotted in Figure 4 and Figure 5 respectively. The GENCO had 6 generating units each with different operation characteristics shown in the Table 4. According to the algorithm, the model was trained for 150 episodes and each episode had 2,400 steps. Each step returned a reward value which was summed to obtain an overall episode reward. Figure 5 shows a plot of episode reward against the episode number. The training was targeted to achieve at least average reward of 6,300 for better results. Successful training of the agent. The trained agent is applied in offline simulation to verify the agent's capability. In this scenario, the market clearing price and allocated energy are acting as inputs to the agent, and the agent gives optimal schedule. To justify the results, trained agent was run in 3 cases. Case 1, the model was trained to meet the expected/predicted spot market allocation. Table 6 summarizes the results obtained under 3 cases. Case 1 had the highest operating cost as compared to Case 2 and 3, this is because large amount of energy was being generated, hence some units were operating under loss. The most optimal solution was under Case 3, in which the operating cost was reduced and more power was being generated at instant that the clearing price is higher, thus making more revenues. The Case 3 made profit 1.5 times that in Case 2 and 1.09 times that in Case 2. The profit generated is increasing with increased energy price provided that the generator operation cost didn't reach its optimal value of operation. This was shown by the unit G2, as compared to other units, its generation was following the MCP nature while others were constant. I.E. higher generation was achieved at higher market clearing price provided that the total generated power doesn't exceed the spot market allocation. This can be proved by considering Figure 4, Figure 5, and the Table 5. At the time between 7 to 19 hours, the market clearing price was high, this made the generated power to increase, as shown in Table 5, in similar fashion as that of Figure 4. Conclusion. In this paper, deep reinforcement learning was used to find optimal scheduling to solve the profit-based generation unit scheduling of the GENCO operating in deregulated electricity market. The Deep Deterministic Policy Gradient algorithm is used to train the agent. The GENCO is assumed to operate under pool market without bilateral contacts of power supply between the GENCO and consumers. The important data input are predicted spot market allocation for the GENCO and the market clearing price 24 hours, day ahead, of time. The method can also be applied in very complicated scenarios where there is larger number of constraints and many generation units.